Just before we start, I think Labarre.
I just want to say, because I won't be here when your session finishes, because I have to go and host the staff sherry party at Churchill College. It's the first of a never-ending line of things this afternoon. But I just wanted to come in and say thanks again to you all for participating, and particularly the organisers. I think it's been a superb meeting. The fuel this week has just been terrific, and Mike, Daniel, Vincent, and Katrina for this meeting have done a fantastic job. So I hope you've enjoyed your week and finished with a flurry. But Mike, and thank you very much indeed. Really grateful to you. Okay, so just two more to go.
Thank you. So this is going to be a talk about a formal model for inferring phylogenetic networks in the context of genealogies. So we heard about phylogenetic networks yesterday. We had some nice talks about that. And the goal in reconstructing haplotype networks is very similar, except that we're considering genes instead of species. So the goal is, given a set of genes, to represent all the shortest evolutionary relations between those genes. There's already a number of existing methods for building haplotype networks, and I've listed a few of them here in no particular order. But they all rely on the same principle, that is, build a graph, then try to use some methods and local heuristics to reduce the complexity and size of the graph. So it's basically building the graph directly from the sequences. And another technique that's been used in phylogenetics is to build the graph not from the sequences but from the trees. And this is a method that has been also proposed by Cassens et al. In that context, which consists in generating all equally most parsimonious trees on your genes, and then try to merge those trees somehow into a graph in the most compact way as possible. So I'm only going to deal with the second step here, that is how to merge those trees into a graph. So before I go on any further, I'd like to stress that those trees have a particular structure, in that they're arbitrary actually. So they're undirected, unrooted. All leaves are labeled, but internal vertices may be labeled as well, and there is no constraint on the degree of internal vertices. So you may have internal vertices of degree 3, 4, 5, and so on, but also of degree 2. This is because we want to model branch length using paths instead of weights. So if you have an edge of weight k between genes A and B, you're going to replace it with a path of length k. So this is an example of how Cassens et al.'s method works. This is taken from their paper. Suppose we are given those 3 trees here. We're going to try and identify what they have in common. So it can be fairly easy seen that there is the same path from C to D in all those 3 trees. So what you want to do is to assign labels, the same labels when you walk from the path from C to D, so that the component will be the same in all 3 trees. There is another common thing in those 3 trees, which is a path from 2 to A of the same length. So I'm going to assign the same labels to vertices encountered when walking from 2 to A in all 3 trees. And then I'm kind of stuck because there is no big structure in common in all those 3 trees. So I'm going to try and find out what do 2 trees have in common. And in particular, you can see that there is a common path from vertex E to vertex 5 in tree 1 and tree 2. So I'm going to assign the same labels just as before. And here I can assign the same labels to those 2 vertices, but then I'm stuck because I don't hit vertex 5. So I'm going to leave that vertex alone for now. And you can do the same thing with a path from F to 2, which is common to both tree 1 and tree 3. And then you can do the same thing with a path from vertex B to vertex 2, which is common to those trees, that tree here and that tree over here. So now that I've labeled everything, what I can do is take the union of the pairs of labels and directly build the graph. And this results in the graph that is shown here, which contains all the trees that I had to start with. And typically you just remove the artificial labels that I've been adding, and you have this graph. And if you remove an appropriate set of edges or vertices, you can reconstruct all of the input trees that you had to begin with. So they tested their method on simulated data against the methods I presented on the first slide, and it seemed to perform quite well, but there is a number of problems with that method. In particular, it's more like a heuristic with an unclear objective function, because it's not very clear what they're trying to optimize. Moreover, it is order dependent in that the quality of the solution will depend on the order in which you assign those red labels on the trees. So what I like to do here is to report on a formal model that I propose to use to solve their problem, and some preliminary results that I've obtained on this problem. So if we're going to get formal, we're going to need definitions, but don't worry, there won't be too much of them. So I call G an NK graph if it has n vertices, k of which are labeled. So in particular, all leaves will be labeled, and the label set we're going to use will always be the same, namely the integers ranging from 1 to k. And I say that G is a common supergraph of a given set of NK graphs if each of the input graphs can be reconstructed from G by removing edges. And it is a minimum common supergraph if there is no other graph with the same property. This will be clear on the following example, I guess. So consider those two trees. They are 7-4 trees in my terminology. You can see that G1 is a common supergraph of T1 and T2, because if I remove the red edges from G1, then I can reconstruct T2. And if I remove the appropriate set of edges from G1, I can also reconstruct T1. But it is not minimum, because G2 is also a common supergraph of T1 and T2, and it has fewer edges, namely 7 instead of 10. And this one is minimum because those two trees are not isomorphic. All right, so the problem is clear. It is that of finding a minimum common supergraph of a set of partially labeled trees. So as input, you're given a set of partially labeled trees and n vertices k of which are labeled. And the problem is to find the minimum common supergraph of those trees. So some results I've obtained so far in this problem is a polynomial time algorithm for two trees that are of a certain class that I call restricted, and I get on to the next slide what I mean by that. The algorithm remains polynomial if only one of the trees is restricted, and then I use those results to derive an exact exponential time algorithm for two arbitrary trees. And it's written here that those results apply directly to graph, and we'll see how we can use that in higher dimensions. So I say that an NK graph is restricted if there is no edge between unlabeled vertices. So every unlabeled vertex has labeled neighbors only. And what good is it to consider those trees when we want to solve the merging problem? Well, the nice thing is that if I'm going to pair up two vertices in those two restricted trees, namely those two vertices in red, well, I know exactly how many edges I will have in the resulting common supergraph. Here I have labels 1, 6, 3, 9 as neighbors of that red vertex, and here I have 1, 3, and 7. So if I just take the union of the labels of the neighbors, then I get the number of edges that will be in the subgraph that is shown here. So you have those 4 edges in green that come from the first tree, and then 1 edge in red that comes from the second tree. So it is easy to see that if you pair up two unlabeled vertices from those three, you just have to consider the size of the union of the labels of the neighbors. It's kind of a complicated sentence, but it's not really complicated at all. So we have that function that gives us the number of edges in the resulting subgraph, and then all we have to do is to use the linear assignment problem to solve to find the minimum common supergraph of those two trees. So the idea is to build a complete bipartite graph with vertex classes, the unlabeled vertices from T1 and T2. So you saw yesterday what a bipartite graph was. And we assign weights to two edges in that graph according to the function that I've shown on the previous slide. And then you just have to find a minimum weight perfect matching on that graph, and this is a classical problem which is solvable in cubic time. So if only one of the trees is restricted, what is there a problem? Actually, there isn't. The problem remains solvable with exactly the same algorithm, because the number of edges that will be in the resulting subgraph will be exactly the same as before. But you have to add the edges that connect two unlabeled vertices. And since the first tree, which is restricted, does not contain any unlabeled any edge between unlabeled vertices, you cannot reduce this quantity. So in other words, we have no power of edges that connect unlabeled vertices, so we can still use the same approach. And then we can use those results to derive an algorithm that will solve our problem on two arbitrary trees. So since we know how to merge restricted trees, we'd like to get back to restricted trees and use the algorithms we have. So if I take this tree that is not restricted, I can easily transform it into a restricted trees by assigning labels to some vertices. In particular, if I assign any label to those two black vertices, then I get a restricted tree. And so I have to find the minimum number of vertices to label so as to obtain a restricted tree. And this is equivalent to finding a minimum vertex cover on a forest, and this is an easy problem. So the sketch of the algorithm is here. If I get two arbitrary trees, I want to label as few vertices as possible so that either tree becomes restricted, or possibly both. And then I have to try all possible labelings of the corresponding subset of p vertices in the other tree, and finally I keep the best solution over all those pairs of trees. So the solution space is pretty big, but each partial solution is solved in polynomial time, and this is an upper bound on the running time of the algorithm, which can be improved using some Lau bending techniques and pre-processing of the trees, namely assigning labels that are obviously safe. So this tells us how we can solve our problem if we have two trees, but generally we have many more than two trees, and I don't really know how to get an optimal solution if I have to take all the input trees in considerations. But one thing we could do is to define a distance on a pair of trees, which is the size of the minimum common supergraphs that will contain them both. And we could try and find an ordering of the merging processes that can yield a solution. So what we can do, for instance, is we're going to try and merge T1 and T2, which we can do optimally. And then we get a new graph, G, which is the union of those two trees, which is an optimal solution. So it is a minimum common supergraph of T1 and T2. And then we can go on using the algorithms I've shown before and repeatedly merge G with the other trees. The algorithms don't rely on the hypothesis that the trees you use are actually trees. So you can use directly those algorithms I presented before. Maybe there's I don't expect to find an optimal solution by doing that, but maybe there is an ordering in which we can, an order in which we can merge those trees that will guarantee some quality of the solution. And that's it. Thank you for your attention.
As you probably know, the medium network, for example, contains almost parsimonious trees for input and the like. Yes. So why do you prefer to?
In median networks, you may have more internal vertices than you had in your trees to begin with.
Yeah, but why do you not try then to prune those down and make maybe smaller networks rather than to build up?
Yeah, maybe we can get. maybe we can get a solution by doing that, but this is the kind of thing that happens in median joining networks, I think, and there are some data sets on which the methods by Kessens et al. Produce better results than the median joining networks technique. So it seems that they want to have almost parsimonious trees, but they don't want to have too many trees. And it seems that the median joining networks will contain almost parsimonious trees, but maybe there are some trees that are not really relevant for their data, and so they prefer using the technique.